public lecture series. My name is Greg Dick, and I'm the Senior Director of Public Engagement and Advancement here at Perimeter. It is, before we begin this evening, in the spirit of respect and reconciliation, we acknowledge that Perimeter Institute is located upon the lands that have been inhabited by Indigenous peoples from the beginning. We acknowledge the Haldeman Tract, the traditional territory of the Neutral, the Anishinaabe, the Haudenosaunee peoples, the ancestral lands of the Attawandaron people, and the treaty lands and territory of the Mississaugas of the Credit. As settlers, we thank all of the generations of people who have taken care of this land for thousands of years. We are connected to our collective commitment to make the promise and the challenge of truth and reconciliation real in our communities. Tonight's lecture is part of Perimeter's public lecture series, our longest running public outreach program. Perimeter is a not-for-profit organization, and these public science events are part of our commitment to sharing exceptional, engaging science. We are happy to be able to provide this opportunity to our loyal public supporters and welcome those of you that are new to our lecture series. Welcome. Just before we get to the lecture, I wanted to share some exciting news from here at Perimeter. Recently, we announced the launch of the Clay-Riddell Center for Quantum Matter. It's a new research hub dedicated to harnessing the intrinsic and exotic properties of quantum mechanics and to uncover and understand powerful quantum phenomena. The promise of research into quantum matter is hard to overstate. In trying to understand how matter works at the most fundamental level, researchers are laying the foundations for the technologies of the future. The center represents a 10-year, $25 million investment in quantum matter research, made possible by a $10 million founding donation from the Riddell Family Charitable Foundation. Clay Riddell was an explorer, an entrepreneur, and a community builder who received the Order of Canada in 2008 for his leadership and philanthropy. Prior to his passing in September of 2018, he made the decision to partner with Perimeter to make the Center for Quantum Matter a reality. During the October 15th virtual launch of the center, his family acknowledged how important it was to Clay to support what he considered a high-impact investment for humanity. We are profoundly grateful to Clay and the Riddell Family Charitable Foundation for their visionary investment in helping Perimeter advance discovery in quantum matter. You can learn more about the new center by visiting our website at perimeterinstitute.ca. Tonight, I'm broadcasting from our temporary socially distanced studio here at Perimeter Institute, and our guest speaker will be joining us from the comfort of her home. As you watch the lecture, I encourage you to join the conversation online. We are at Perimeter on Twitter, and use the hashtag #PILive to chat with Perimeter scientists and to ask questions of tonight's guest speaker at the end. And now, I am pleased to introduce Dr. Catherine Beauchemin. She's a professor of physics at Ryerson University in Toronto, and the deputy program director of the Riken Interdisciplinary Theoretical Mathematical Sciences program in Waikoshi, Japan. Armed with an undergraduate degree in computational physics from the University of Ottawa and a PhD in biophysics from the University of Alberta, Dr. Beauchemin completed a postdoctoral fellowship at the Los Alamos National Laboratory. There, her passion for modeling the spread of virus infections really took off, ultimately leading her to coin a whole new research discipline, virophysics. This new research stream has allowed Dr. Beauchemin to engage at the intersection of experimental virology, applied mathematics, and physics. Her interdisciplinary approach opens up new avenues for discovery in a world that has become increasingly cynical of science, and specifically of health research. In her talk this evening, Dr. Beauchemin will highlight some of the issues that have eroded trust in health research and explain how a dose of physics may be just the prescription we need. Ladies and gentlemen, let's welcome Dr. Beauchemin. Dr. Beauchemin, how are you?
Hi, good. A little cooped up, but I'm good.
Well, welcome. And so where are you coming to us from?
From my living room in Toronto, and my cat is on the couch there. You might make him an accidental appearance, but yeah.
Well, the cat is welcome at any time. You know, we've been really looking forward to this, so why don't we just get right started? I'll hand it over to you.
Sounds good. Thanks a lot, Greg.
Thank you.
So I'm going to start right away with my disclosure. which says that in the past, I have received consultant fees and research funds from the pharmaceutical companies F. Hoffmann La Roche, AstraZeneca, and Adamas Pharmaceuticals. Currently, my salary and my research funding are from public government sources only. All right, so let's start us up with the scientific method. And even though it's called a method, which suggests that it's a series of steps, it's actually more a set of ingredients that need to be present for something to be considered science. And it's also a way to distinguish between something that is science and something that isn't. And so those key ingredients involve, in particular, having a hypothesis that there is a rational universe and that there exist laws of nature. It requires some skepticism so that if new data comes in, that you're able to change your mind and not just be really camped on the one position. It requires, it's constructed from falsifiable hypotheses and theories. And by that, we mean the way you would construct a hypothesis, that it has to be possible to prove it wrong. It doesn't need to be proven wrong, but obviously it should be possible to do so. It has to rely on honesty and transparency, where you correctly state everything that you did and you report accurately what you obtained. And finally, the ability to independently verify the facts for oneself. So you don't need to trust other people. You can listen to what they say they've done, and you can go and test it out for yourself and verify for yourself that that's true. And that's mostly it. But the truth is, of course, there's a lot of experiments that we can't conduct ourselves. For example, I don't know about you, but I don't have a large hadron collider in my backyard. There's just the one. And so if you wanted one, of course, another one can be built, but it will require a lot of money. So in places where the research is not easily reproducible independently, then we actually have to rely on trust. And so that's where trust comes up in science, is when it becomes difficult for you to independently verify the findings, right? But the problem is trust is a bit of a problem these days, and in particular in health research. Now, this is pre-COVID. This is a paper from 2014 where they interviewed people in a number of countries. And the question they asked to them was, all things considered, doctors in my country can be trusted. This is the percent of people who agree or strongly agree with that statement. Now, Canada is not in the list, and that's because it was not one of the countries that they surveyed. I've retained the highest ranked and the lowest ranked country. But you see that even in the highest ranked country, actually, only 4 in 5 people feel that their doctors can be trusted. That's still the 1 in 5 that thinks, you know what, I don't think I can trust my doctor. And it's very concerning because doctors can be responsible for things that are life and death. Literally. So trusting that their advice is sound is rather important. And it's that level of confidence, 83%, is actually not that high when you think about it. So where are some of the negative public impression coming from? And they tend to fall into 3 categories mainly. The fact that experts always seem to disagree. And I'll give an example of that in a second. The idea that the experts keep changing their mind. Here we can think of 1 year, butter is dangerous for you, but margarine is better, and the following year is the opposite. Or perhaps more, what comes to mind more these days is, well, at first we were told masks can cause more harm than good because you'll infect yourself touching it. And then later on it's, now we need 3 layers and put that mask on. So there really does seem to be this thing where the experts are changing their mind. And also the experts seem to have an agenda, whether it be profit or politics or even social engineering, which is kind of well-intentioned agenda where you say stuff to people to induce them to have a behavior that you think is for the public good. So these are the impressions that people have that make them distrust the public health people. So let's talk a bit more about where that might come from. So this is an example of expert disagree from our recent past, and that's the whole debate over hydroxychloroquine. So this was a hearing in the U.S. House Oversight and Reform Subcommittee on the coronavirus. And here, Representative Lutkenmeyer is asking Dr. Fauci about a hydroxychloroquine paper that suggests that hydroxychloroquine would be effective against SARS-CoV-2, which is the virus causing COVID-19. And he asked Dr. Fauci what he thinks of it. And Dr. Fauci says, well, so that study is a flawed study. And I think anyone who examines it carefully sees that it is not a randomized placebo-controlled trial. To which Lutkenmeyer responds, it's been peer-reviewed. To which Fauci says, it doesn't matter. You can peer review something that's a bad study. And there's 2 main problems here. Number one, they're saying that the peer review process, there's the problem with a peer review process. So even though 3 experts says that this paper is fine, it's meeting all the criteria, Dr. Fauci says, well, actually, anyone who examines it would see that it's not randomized placebo-controlled, so it is not a good study. Yet possibly as many as 3 reviewers said that it was. So there's this one problem where there doesn't seem to be an agreement on what constitutes a valid study, or it's like a post after the fact reevaluation of this. The other aspect of this is, of course, Dr. Fauci will come later and make statements about why you would make the following recommendations. And you would say that these are based on peer-reviewed scientific literature, which of course is the same thing that we can say about this study. So why is the studies that Dr. Fauci chooses, those are the correct studies, but the other studies that are also peer-reviewed and otherwise equal are less valid, right? So this type of messaging doesn't help the case that peer review, which should actually catch things like that, sometimes doesn't. So we're going to look a bit at some of the causes behind the problem in peer review in health research. So one of them is the problem of research ethics. So this is the top 15 authors of scientific papers ordered by number of papers retracted. So a retracted paper is a paper that you submitted for evaluation, peer review, it's been peer reviewed, it's been accepted, published in a journal, and then retracted after the fact when a problem was found. And the problems can be varied. It can go from this person used the same data in multiple papers to all the way to this person falsified the data and played with the image, in Photoshop and made it look the way they wanted. But what you can see here, and you could go look at the full leaderboard that Retraction Watch keeps on their website, and they give there the details of what was the problem with each paper. But what you can see, though, is that 60% of this top 15 is actually in medicine. I also like, as a physicist, to point out that none of them were physics. But more importantly, there really does seem to be a problem that is happening within medicine, more so than in other fields. So this is an example of how these things come about. So this is a study where they look at 363 published articles. So these are peer-reviewed published articles that were testing the standard of care. The standard of care is if a person has the following condition under the following additional things, this is the treatment that you should follow, right? So these are what the standards of care are. And out of 363 articles, when 146 of those were actually reversed. So when study was done about the standard of care, it was found that it was more harmful than good and had to be reversed. And I can show you one example of this. So here's an example where the practice was implanting gentamicin collagen sponge, and it's to prevent infection after a colorectal surgery. And this procedure has been used in millions of patients since 1985. And it was based on a single center randomized trial which found a 70% decrease in the infection when you had this practice in place. But then a later paper, so an example of a reversal, a later paper was based on a larger multi-center phase 3 trial, and it found instead significantly more infections, more visit to emergency, and more hospitalization. So if we just didn't do this extra step, we would have fewer infections. So doing this extra thing was actually causing more harm than it was reducing. But you might ask, how is it that 2 different studies found 2 opposite findings? And we'll come back to that later, and some of it has to do with math. And here's another review. This one is at the level not of medical practice, but at the lab research level, right? So the more fundamental level. And this is a review paper of review papers where they looked at various fields and some of the issues. So this is the first one you see here is based on a Ioannidis 2009 paper, which was looking at microarray data, which find that 16 out of the 18 studies that they looked at could not be reproduced based on the raw data. Another one from General Biology, 2011, 75% to 80% of the 67 studies they looked at could not be reproduced. Here's one in oncology, 90% of 53 studies were not reproduced, right? You can also look at other types of problem. Here we have an over-publication bias. So this is stroke in animals. And they found only 2% of the studies were negative, which means that 98% of the time when you went looking for something, you were able to confirm it. Now, any one of us who's been a human for any amount of time, we know that that's usually not how life works, sadly. A lot of time, we tend to fail at least as often as we succeed, but certainly 98% success is not what you would expect in basic health research. And so what that suggests is one of two things. Either if you have a negative result, it doesn't get published. So even though people are doing them, they're not getting published. It could also mean that some people are pressured then to making their result positive so that they will get published. But it also means that if I don't see the negative research, then I'm bound to maybe repeat it. So if I don't know that somebody's already looked there and found nothing, I might go looking as well and finding a negative result, knowing that I can't get published, I'll just move on. So the same research could be done over and over again, trying to undo this. So I've talked about some of the main feelings that people have, that where their negative impressions come from. But here's some of the reasons now that we've seen some examples. One issue that I see a lot is the idea of disregarding data in favor of opinion. So you go in saying, well, I think A does B. And then you do the experiment and it's not quite how it runs out. But you think, well, there's a lot of variability. Why don't I do the experiment again? And lo and behold, now A causes B. And you're like, okay, that's it. I can go and publish. So that's an example where I had a belief before, the data didn't quite match, but I know there's a lot of variability. I'm just going to do it again. There's generally an aversion to basic exploratory research. So if you go for health research funding, what happens is normally, it's quite different from physics. You would go in and say, my research will show that A causes B, or that A is affected by B. And what that means is that now your research plan is to actually show that. Whereas in physics, we have more something like, well, I'm just going to figure out how A works as best as I can and get as far as I can with that. And here's what I plan to look at, right? So there's a difference here in the way it's angled. And it also means that there's then more pressure to find what you were looking for. There's also, related to that, an aim to prove rather than disprove the hypothesis. Normally, what you would want to do is set up an experiment that could show that your position is false, right? So that's what you aim to do. You aim to disprove. Remember the falsification at the start. And also, we often find major flaws in the study design or the analysis. So we had the example of the non-randomized placebo-controlled trial that we saw earlier that Dr. Fauci was complaining about. But actually, if you look closer at these, you'll find that a lot of them come from a poor understanding of math. And to illustrate that, I want to take you back to your high school days. And this is pre-COVID, possibly for some of you. So that's a better days, at least in that respect. And if you think back on your textbook, if you think about your physics textbook and your biology textbook, if you open your physics textbook, it was full of equation. But if you open your biology textbook, it was full of words and pictures, right? And that actually carries through all the way through the research field. So in physics, we'd observe a phenomenon, we'd analyze it, and then we'd come up with an explanation. And that explanation would take the form of equations. And these equations would then allow us to check whether, in fact, our observation match what we think we understand about the system. But it also allows us then to use what we learned from the experiment and our model to actually predict the outcome of an experiment we've not yet done. So, for example, I can drop the apple from lower and see what its height's going to be over time. And it should match my model, or it will not, which allows me then to adjust my model, right? So it's constant back and forth. In virology, though, so this is true of biology in general, but we're going to talk about virology here. You can observe your cell infected by virions. And by the way, virions are a virus particle to the same extent that photons are light particle. So we have the virions here coming out, so you can measure them as a function of time. And already you can see a difference. The lines are straight lines, just meant to aid your eye. It's not based on a model. When you come to the modeling or explanation part, it's all word-based. So, when a cell's infected, it produces that much virus. And then if you want to see what happens if you put twice as much virus, you say, well, I'm going to need additional funding for that. Now, if you think about it, what we're really saying is, let's run the space exploration as follows. We're going to take stuff and we're going to throw it at the space and just keep throwing until it goes where we intend. And so that's, of course, very costly and wasteful. And it's really more akin to trial and error than really advancing systematically our understanding. And it comes from the lack of math. So that's where my research, so I'm trained in physics, and what my work is basically is to translate what is believed to be understood by virology and translate it into mathematical expression, a physical model, and then play it out to see whether indeed what people think they know matches experimental observation. So I'm going to talk you through both the math aspect of this and the virology aspect of this. So the way a virus infection works is as follows. You have an uninfected cell. When a virus enters that cells become infected, and it first enters what's called the eclipse phase. And it's the eclipse the same way we have eclipse in astronomy. It's the idea that stuff has disappeared, right? And in this case, it's the virus you put in has gone into the cell and it's just gone. And for now, you don't see anything. And after some amount of time, what's happening inside the cell, of course, is the virus is being unpacked. It's starting to harness the machinery inside the cell to make copies of itself. So it's using the cell as a factory to make copies of itself. And so after some amount of time, tau e, the factory is set up, and now it can start cranking out virions. So that's like at some fixed rate, let's say 3 virion per hour per cell, for example. And so at some point, because of that process, the cell is going to end up not being infectious anymore, either because it died or because it shuts down production. And it could be because, for example, the production of virus has exhausted the cell, or maybe the byproduct of that is toxic to the cell environment, and eventually the cell can no longer produce virus. So the virus has been produced at some fixed rate, and that virus over time will either go on to infect another cell at some rate, or the virus will be cleared. Now, the clearance of the virus here refers to the fact that the virus loses infectivity over time. And so that's, if you remember early on, we were very concerned about how long live virus can stay in our groceries. How long do I have to leave my groceries out before it's safe if there was virus on it so that this virus is no longer infectious? That was a lot of the questions we had early on in the pandemic. And that's exactly this parameter. So estimating the rate at which the virus will degrade enough that it's no longer able to cause an infection. So now we have a mathematical equation. I mean, I'm hiding it behind pictures and Greek letters, but you can trust me that it's there. And if you have a question at the end, you can ask me to show you the math. But once we have the mathematical model, what we do is we actually use it to simulate experiments that people are able to conduct routinely in virology to find a set of experiments that independently can give us information about each of the parameters. So these are the two experiments we identified. This one is called the single cycle assay, and this one is the multiple cycle assay. And they differ only in their initial condition. In this case, I start with a certain amount of virus that is enough to infect all cells. So it's about 3 infectious virus per cell. So all cells get infected roughly at the same time. Virus production takes off as the eclipse phase. So this would be the eclipse phase. Cells start producing virus. Now all cells are producing virus. So that's why you can see this steady state, because the cells are producing virus at the same rate as the virus is being cleared. And so you can read right off this graph that the eclipse phase is approximately 6 hours in this case. This is an influenza. This is real data from an experiment. Over here, this is the multiple cycle assay. It differs from the single cycle only in the initial condition. So you start the infection with maybe 10 infectious virus per 1 million cell. And so what you end up is these 10 initially infected cells produce virus that infect other cell, that produce virus that infect other cell, and you can see the spread of the virus within that cell culture. And with this, here that steady state is for the same reason. Now all your cells are infected. So the width of that plateau tells you how long the cell is infectious for. And then once the cell dies, you can see now this decay, and this decay is the virus clearance rate, that parameter that we wanted to know early on. The steady state here, P is balanced with C. So from knowing the clearance rate, we can determine the virus production rate. And finally, the upslope depends on all the parameters, but because we know the other ones, we can now estimate beta, the infection rate. So that's how the system works. And so we went ahead and put it into application. So this is for influenza, but I'm not going to talk about the specifics of the problem, but mostly tell you that this is a wild type strain of influenza and a drug-resistant mutant where we've put in the mutation by hand ourselves in the same background as the wild type. So they differ only by 1 mutation. And so this is the data for the single cycle experiment. This is the data for the multiple cycle experiment. And the black and red line is the predictions, the fit from our model. And so here what you can see is that for each parameter, we're able to extract a value. So for example, here we see the eclipse phase is about 7 hours for the wild type, plus or minus 1 hour. So what's powerful about this method is that it allows us to extract how the mutation affects every single aspect of the virus replication cycle. But you can imagine using that in a different way. Instead of a mutant, you can have the wild type and the wild type plus a drug. And then you could see exactly what aspect of the virus replication are modified by the drug and how the dose that you give of drug modifies by how much it modifies each parameter. So you can really map dose to effect. So this is great, but you don't have to believe me. Maybe this is not the correct parameters. I say I've extracted them, but who knows? So what we do then is we use this model to predict the outcome of an experiment we hadn't yet done. And the way we did that is we decided the experiment was going to be a competition where we're going to make those two strains fight it out. So you're going to have the wild type and the mutant. You're going to pour them onto the same cell culture, and you're going to find out which one wins and by how much. And so that's the experiment that we used our model to predict. And here's the data. So at the bottom here, this is 80% wild type, 20% mutant, 50% wild type, 50% mutant, and here 20% wild type, 80% mutant. And you can see the dashed line is our predictions, and these boxes are the actual experimental data. So you can see that we're actually able to predict the outcome of an experiment that had not yet happened, right? And so this is it. This is the power of such methods. Sorry, that's my cat making noise. So we thought, well, this is great. Let's do this again. Now we can isolate the effect of every single mutation. This is a very powerful method. So we went ahead, same virus, but we introduced a new mutation in it. So the wild type is the same, but the mutant is new. And we, of course, wanted to study the effect of that mutation. So again, the single cycle, the multiple cycle, this is the wild type, this is the mutant. But we also, as physicists, were very curious to know, we had these parameters, we extracted them. They should match between experiment for the wild type, right? Because it's the same virus. And sure enough, here, this is our eclipse phase, still 7 hour plus or minus 1 hour. Awesome. But then we start looking at the other parameters, and it's very disturbing, the picture. And in particular here, you can see that the same strain is more different from itself between our two experiments than the wild type is different from the mutant in this new experiment. So that's very disturbing, of course, because we kind of feel we estimated our parameters correctly, because we were able to predict the outcome of an experiment. But this is bizarre. Where could these be coming from? Could it be our analysis? So we went and looked at the data specifically, and we found that the lower virus production rate that we find in our analysis actually is reflected in the data as a lower virus titer peak. Remember, the virus production is the height of the plateau. And you can see, for example, between the two experiments, black is here, blue is there. There's definitely a decrease. So our parameter matches what is in the data. Same thing for the shorter infectious lifespan. This should be the width of that window here. And sure enough, it got shorter between black and blue. And so it really does look like our parameters are matching what's actually in the data. And what's actually happening is that these parameters are, the measurement of these parameters is changing between experiments. And that means that maybe these experiments are just producing random numbers. And that's very disturbing because it's a very expensive way to generate random numbers. So we thought, where does that leave us? So we dug a little closer, and we found that there were some parameters that varied between the experiments, but were consistent within a given experiment. So here you can see this is the old experiment, and this is the new experiment. So in this case, this parameter is experiment specific and not strain specific. And you can see that it's consistent. Both strain, we extract the same parameter, but it differed between the experiment. And here's another two examples, right? So what this suggests is that the parameters between experiments can shift, like the cells can be a bit more conducive to virus production in the new batch of cells than in your old batch of cells. Even though it's the same cell type, the batch could be different. And what we think that could mean is that instead of having the virus production always be the same between experiments, it's more that if strain A produces more virus than strain B, that would remain true. So in other words, the relative property of a strain, so let's say A is 3 times the standard strain, would hold rather than the absolute, that A is equal to 5. And so, okay, where does that leave us? Well, our predictions work. And so that's great, but only within one experiment. And what's happening is that the inter-experimental variability is often greater than the changes we're trying to study. And we really have two options here. We can either express our parameters relative to a reference strain. So whenever you do the new experiment, you have that standard strain in there to compare back to. So you always express everything relative to the standard strain. And or, because you could do both, you can also try to figure out what are these sources of variability. Can we figure out what they are and include them in the model, and also measure them experimentally so we can always take them into account. But you can see that either way, we're going to need mathematical models to do this. So basically have a physicist approach to the problem if we're going to tackle this problem. So we thought that was a good story. I hope you agree that this was a good story. We had some information about the mutant and some way forward to address the problem of experimental variability. And we thought so, but we were talking about peer review earlier. The reviewer of our paper did not think so, and in fact recommended that our paper be rejected, and it was, which we appealed. But this was the comment that the reviewer made. Further, a significant portion of the manuscript examines the issue of interexperimental variability. I find this to be a major limitation of this work, since this type of variability should not exist if proper techniques are used. In general, variability of this nature in biological systems makes it difficult to believe the results. There should be little to no interexperimental variation if proper techniques are used. Were two different people performing these experiments? It is unlikely that the variation is true or biologically interesting. So what the message here to this review to us is, when we see variability, we don't trust your paper and we'll reject it, which, I could say, oh, well, I guess I have to make sure I have very little variability, which should not be the correct conclusion. And the other message here is that proper technique means having the same person doing a same day with the same equipment. It's like saying that we can only confirm the mass of whatever particle when Jane is in charge. So it's concerning because it means redefining variability, which redefine the result significant. And I'm going to walk you through like a small thinking experiment about this. So here we have a Jane, and she's doing an experiment, and she's doing it all on the same plate on the same day, all by herself. And she's comparing drug A to drug B and finds that drug A is more effective at suppressing the virus than drug B. And it's very small variation because she's doing it all herself the same day, same cell culture. Here, this other lab is doing it separately, three separate people, three different batches of cells, different reagents, and so on. And what that means is that you end up with a lot noisier data. And now there's not that clean separation between red and blue. And you can say, well, actually, drug A and drug B are not statistically significantly different. Now, you might think these two studies are in conflict with one another, but they really aren't because they're not asking the same question. Here, this is equivalent to saying, I found that this drug was effective in Mary between the hour of 9 and 10 a.m. when Jane is doing the measurement, right? And here I'm saying, well, I gave the drug to a bunch of people and I didn't find a particularly significant effect. So these are two different questions. This drug really is effective when Mary is testing it in Jane, or was it the other way around? And whereas this one is more widely applicable result, right? And so, but that also means that if somebody wanted to verify this experiment later and did it again, it would be, let's say, Greg is doing it and Bob. They might, because there's normally noise in the population, they might get the opposite, where the red is down here and the blue is up here. And what it would seem as though, these results are in conflict. But in reality, they aren't, because again, they're asking a slightly different question. This is no longer about Mary and Jane. This is now about Greg and Bob. And so both studies are correct, but their field of applicability is very narrow, much more narrow than people would think. And so in the end, what I hope you take from this is that when you express a system, a biological understanding of a system in terms of mathematics, it allows you to realize how much detail you need to really fill in all the gaps. And in particular, it'll show when there's knowledge gap as you start building that model as an equation instead of just a verbal explanation. You'll see that there are bits that you're missing. And that's happened to us a lot of time. And it's very exciting when it does. And as the process of replacing the words with numbers, it allows you to detect systematic errors with your experiment or with your data, to distinguish between noise and a new phenomena. And to predict beyond just the experiment you did. So there's more bang for your buck, as they say, right? So there's really a lot of value to bringing a mathematical description to a scientific system, and it could in particular benefit health. So for this part, I want you to take home is the idea that being skeptical is healthy, and being absolutist is not. So using terminology like always, never, infallible, it should really probably never be used in science. These types of terms are just too strong. And and rarely accurate. I've probably convinced you that health science has some house cleaning to do, and that physics and math is an essential part of addressing a lot of the issues that we see in health science, and that virophysics in particular can offer a lot of solutions. Now, it's not ending here, even though it says take-home message. You're not going home yet, or maybe you already are, like me. But I wanted to talk a bit about COVID because, well, it's kind of on everybody's mind. So I just want to give you a quick intro to how to look at data when it's presented to you with a critical mind. And so let's introduce some very basics, which are the terminology of reproductive number and serial interval. So the reproductive number is the number of people each individual will infect on average over their infectious period. So it's from the time you start being infectious to the time you stop being infectious, either because you've stopped shedding virus or you died or you've recovered fully. And so here in this example, that's 3. So each person is infecting 3 people. Now, the other term is the serial interval. It's the distance of time between 2 such generations, right? And it's a bit more complicated than that, but I want to keep the language simple here. And in particular, I want to say that what I'm going to say next actually is not sensitive to the subtleties that I could correct. So here, this is the serial interval passes between each generation. And so we start with 1 individual, multiply by 3, we have 3 infected individual, multiply by 3, we have 9 infected individual, multiply by 3, we have 27, right? So there's a product at each cycle. So let's go ahead and plot that to see what that data looks like. So this is graphs we've all too familiar with now. This is the total daily new cases. This is fake data. And then on the x-axis is the days since the first case. And so here you start with 1, and then 3, and then 9, and 27, and so on and so forth. And here I've chosen an arbitrary serial interval of 10 days. And so this is what's called a linear scale graph. So here, this axis is linear. And what that means is between each gray bar, it's plus 50, plus 50, plus 50, plus 50. Okay, so it's plus is the equally spaced. And so here, when I multiply by 3, it's 1 to 3, 3 to 9, the spacing is starting to increase. And so I can see the distance between points on this scale get further and further apart. Then there's the logarithmic scale. So this is the exact same data on the right, but here I've changed my y-axis only. My x-axis is the same as before. My y-axis is now what's called on a logarithmic scale. And so here, between gray bars, it's not a plus, it's a multiplication. So this is times 10, times 10, times 10. And since my progression of infection was times 3, times 3, times 3, these products are going to show as equal spacing in that scale. And so what it allows me to see right away at a glance, because we're very good, our eyes very good at picking up straight lines, what we see is that this times 3 has not changed. So through the entire period of day 0 to day 50, each individual was infected 3 other individuals. And we can tell that because it's a straight line, which means it's always the same product between pairs of points. Here, we can't tell the difference. We can't see whether there's the same progression between these 2 points as these 2. And your eye will also be confused to think, well, things really seem to have surged on day 30. And you'll hear that language on the news. There's a surge, there's an uptick, right, around day 30. And sure, it's true. When you multiply a larger number by 3, you get an even bigger number. And so there is that effect happening. But really, nothing happened on day 30. It was business as usual. 3 people infected 3 people, but we were starting to have a lot more infected case. And this becomes more true when you start going a little further. So here, instead of day 50, I'm going out to day 100. And now you could really see, it looks like things really took off on day 75. And it's not clear now. All the early kinetic is gone. It's not visible. And all I see is the latest cases, right? And it's at 60,000. So that's a scary scenario. And that's how quickly, so 100 days, how quickly, if each person infects 3 people, how quickly you get to 60,000 new cases per day. But what you can see is that here on my log scale, it stayed like a straight line. So I can immediately tell by just looking at the data on the log scale that we still have 3 people infected 3 people, and that hasn't changed. And so this is what's great with the logarithmic scale. Now there's another thing that's great with the logarithmic scale is that you can pick up on change in the reproductive number. So let's say we introduce some measure, be it mask or distancing, and we want to know if it's been effective. So if we're looking at a linear scale, here the difference between above and below is that here I kept 3 all the way through, and here at day 50, I changed the reproductive number to 1.4. And if you're looking at this data, if this was real data, you'd say, well, you know, there maybe was some error reporting, but this looked like a single exponential, right? And I might not know that what's happened is that there's been a change right here, because this might not be different than normal noise. But if I look on the log scale, I can see path, path, there's clearly 2 straight lines. And so I can really tell, for one thing, the day on which it happened, and whether it's resulted in a reduction or an increase in the number of secondary case each case causes. So if you want to know if your measure is having an effect, this is a great scale to actually see that with your own eyes. And I'm not going to make you just look at this fake data. We're going to go look at real data. So this is a slide from the Public Health Agency of Canada. They put out these slides. They're public on the website. Anybody has access to them. And this is their October 9 report. And what you could see here is a few issues that I would like to point to. They're using a linear axis, which is problematic for the reason I said. They're using the language accelerate. We've learned why that's a bit misleading. If you're looking here, it's really not clear whether we have 2 exponential or whether that's a single one. And really, we'd want to turn that into a log scale to know if the slope has changed. The other thing you might notice is that they're doing a 7-day moving average, but they're not recentering it. So it means that they take this day, for example, and take the average of the last 7 days, and then they put the curve here, which means that instead of shifting it by 3.5 days, where the center of the average is, they put it at the day where they're doing the averaging. So you end up shifting the curve actually forward in time. And so you're behind on picking up on patterns. You're 7 days behind picking up on new patterns. And I've seen, usually when I was doing my graph, I'd say, oh, there's an uptick, and then they'd report it a few days later. So it really does seem to affect the way people perceive the data. Now, let's look at this log scale. So this is same data. This is all public data. So I went and got the data from their website. This is their same data. You can see it looks the same. The red dots, the blue bars are now the red dots. And this is case per day. And here down there is the death. And over here, I've put this on a logarithmic scale. And already your eye can pick up that this looks like a straight line. Looks like a straight line. This looks like a straight line. So let's zoom in and see what I'm talking about. So here, this is what we did. We thought, well, it should be a series of straight lines. Let's do a bunch of linear regression. And you can see now, especially with the blue line put right on top of the red, that it really does seem to be a series of straight line, and allows you to then match some of these events with perhaps some measures that we're taking. Now, this is for all of Canada, and measures are not taken at the countrywide level. But in particular, again, around August 30th, when school started, and there was a lot of reopening in Quebec and Ontario, and October 3rd or thereabout is when Quebec and Ontario closed back a lot of things. And so it really does seem to line up. And it also, unfortunately, suggests that we're still growing. It's not been enough to actually stop the growth. So I think I've got a bit more time. I'm going to go ahead and tell you one more story, which is about the death, which you see right here. Now, I just want to go back to the raw data so that the lines don't distract us. If you look, the distance between the black and the red curve, so this is daily death and daily cases. The distance is about 1 gray bar. And remember, 1 gray bar is 10-fold. What that tells me is that 10% of the cases that are reported result in death later. And in fact, the correct number is 9.5%, and it happens 12 days later, okay? And that was early in the pandemic. But if you look over here, you actually see that it's dropping by 2 gray bars. So that's times 10 times 10, so that's 100. And so that would be 1%. And in fact, the exact number is 1.5%. And now the delay is 22 days. And what that means is if I know today how many cases were reported, I can tell you how many deaths there will be 22 days later, and it will be 1.5% of these numbers. Not the reported number, but the averaged out numbers. Okay, so that's the power of this method. Now, I think I'm going to take a few more seconds to explain to you perhaps why this happened. So why did we end up between the 9.5% death early on to 1.5%? There's been a lot of speculation about what that could be. Could it be that we got better at controlling the virus? Could it be treating people with the most severe cases? Could it be that it's because the virus got less infectious or less dangerous? Could it be that it's the age group that are being infected? And I'm here to tell you that it's the age group that can explain most of the variability, but don't take my word for it. I'll show you the data. So I took the database. This is, again, publicly available data. This is for Ontario. And I've taken all the cases that were either resolved in recovered or dead. And for each age group, I checked how many deaths per reported case. And you can see that if you're in your 80s, you have a 1 in 3.7 chance of dying if you're confirmed as COVID positive. In your 70s, it's 1 in 6.8 chances. If you think about that, Russian roulette is 1 in 6. These are not good odds. But even at the lower end of that spectrum, that's 1 in 6,800. And I don't know, if there was a 1 in 6,800 chance that my child dies if they go on a roller coaster, I don't think I'd let them ride that roller coaster, right? So even if the odds are small, they're still large, relatively speaking. And in fact, the other thing you can look at in the data is look at the age, the proportion of the cases that are of each age group as a function of time. And you can see that indeed, early on, the people in their 10s and 20s were relatively low, and they're relatively high now, whereas the people who were in their 80s and 90s were high at the start and are fairly low now, right? So there's been that shift. So if this is the age of the people getting infected, and this is the chance of getting infected, of dying if you become infected, I should be able to predict the death rate based on the age of the people becoming infected. And this is that prediction. So the orange dots are the actual death, and the blue dots are the predicted based on age only. So if I take the age of the people that are infected on that date, I can see what proportion of them will result in death, and that's my prediction, and that's the truth. So you can see that early in the pandemic, I'm a little bit off. I'm a little bit underestimating, and later now, I'm overestimating a bit. So that suggests that there's another factor that plays a role, but that you can see that age explains most of the data. And you can see that 9.5% and 1.5% and where that came from and the transition between the two. And it really looks like 1.5 is about steady now. So I'll leave it at that for now to give you some chance to ask questions. And I want to leave you with the following, that bad science and health research is actually giving all of science a bad reputation. I think it's healthy to be skeptical about medical and health research, but you should be even more skeptical of random websites. It's not because there's issues with medical research that you should trust random other information. A map description is going to be required to tackle a lot of the issues I pointed out. There exist a lot of solid medical results that you should absolutely trust, like old vaccines like mumps, rubella. Go for it. Antibiotics are amazing. They can save your life. Limb reattachment, cast for broken bones. Let's go for this. And there's also, I'm hoping, a change in messaging from health research that has to improve. And in particular, I hope that doctors can do a better job of communicating the degree of uncertainty in the treatment to the patient and take the decision with them, as opposed to saying, do this, it's the correct decision. Instead, given that what we know about the standard of care that can change, it's better to say, this is the state of the art, this is what we think is best now, this is the evidence we have. You can either go with my recommendation, how do you feel, right? And so I think involving the patient is important. And that's most of my message.
Fantastic. Thank you very much. That was incredible. That was a lot covered. I'm looking forward to it. And there's some good questions bubbling up already. And to those of you at home by your keyboards or thumbs on your phone, do send the questions in, #PILive. They'll make it to me, and we'll get through as many as we can. So let's get right started. Catherine, the first one. Where did it go? There. Online question. I've never heard of virophysics before this talk. Do you have a sense of how many people work in this area worldwide?
Well, there's me. I made up the field because I needed to position myself better for grants, being neither a virologist nor necessarily quite what physicists would recognize, because even though I'm a physicist, the system I study is virology. And so it's a bit of a problem. I would say there's a lot of applied mathematicians who are sufficiently applied and concerned about really addressing health issues that they could be considered virophysicists. And there's all the people who were graduated from my lab who went on to work in that field. So I would say maybe 5 or 6 right now. But if we widen the definition, we could probably say about, 2 dozen.
Oh, very good. That's good. Okay, here's another online question from Twitter. How does studying COVID-19 while in the midst of a pandemic compare to other work that you've done in your career? What are the unique challenges that come with that?
So that's a good question. I mean, what I would have to say, because I've been very critical of a lot of things about health research, what I found fantastic is the amount of data that was immediately and publicly available. So not available just to the people who are in the field, who have the right connection, but to everyone, right? Being frustrated with the linear graph, I went and pulled the data from a website. So I didn't have to find the right colleague, connect to them, and acquire the data from them. Anyone watching at home now can go and download. I've asked them to post a reference for all the data sets. You can go and get them yourself and make your own graph, do your own linear regression. So I think that's awesome. So that's new. The idea of having the data so widely available. In health research, a lot of time now, people are required to deposit their data along with their paper when they submit. Which is a great practice. I'm really happy about that. But it does mean that until it's published, you don't have access to the data. So the relationship is different. I'm not working with anyone in particular, and normally I would be. We'd be working together, defining what experiments we want to do, what questions we want to address, and going back and forth with the model and the experiment to make sure we can really tackle that question. Whereas now it's whatever data we have, and if I could shape it, and I hear a lot of other people who are working in that data space who are also wishing that they could do something different with the data. So the fact that I can't shape the data or influence how it's collected to improve some issues is frustrating. But I'm so grateful that we have such a wide access to that data. It's great.
All right, thank you. And another question. Your graph about COVID deaths per reported case is pretty stark. Do you happen to know? Do you happen to know how those rates compare to influenza or other illnesses?
Oh, I wish I had looked that up off the top of my head. It is far higher, but I couldn't tell you exactly how much. I think maybe. Let me guess. No, I don't want to guess. I'm not sure. I wish I could answer that. That's a very good question.
No, that's fair. All right, here's another question. This is going into the math a little bit. The importance of mathematics was clear in your presentation within health research. Can you speak a little more about the obstacles that are standing in the way of solutions grounded in mathematics?
Oh, yes. I'm so glad for that question. So first, thank you so much for asking it. I would say the biggest obstacle is that textbook I told you about from high school, the fact that it has no math in it. The problem is it doesn't change when you go to university. Overall, a bachelor in biology, which is the gateway to all these other, whether it be immunology, virology, all these other health topics, the textbook still has no math once you get to university, or very little, if any. And part of the training to become a doctor, to become I am a medical doctor, biology, wet lab scientist, and health research. All of this training has very little, if any, math. A lot of time, there's the math course for health science, right? It's a separate math course that is less rigorous. And so, if the entire field, all the experts in the field, have not had the mathematics background to understand the problem, it's hard for them to think that that could be a solution. So part of the problem I face and why I made up virophysics is if I show this presentation to virologists, they're not going to take the same thing away from my conclusion that physicists do. It's a completely different reaction. And so to some extent, I think there's a recognition that these problems are there, and there's some things that are being done to address them. And those include requiring people to provide their data. There's some discussion around a problem called p-hacking, which is also related to statistical significance. So there's a recognition that that problem is there, but I'm finding a lot of the solutions that people are thinking of to be really inadequate. And to be frank, I think if a solution will be found, it will be found from within physics. It will be found by having more physicists join me in doing research in virology. And it's been challenging to find physicists who are willing to do health research because I think they feel that it's not quite the same as physics, when in fact, virion, photons, who cares? This is a fun, curious system that we can probe and understand better. And I hope I can convince other physicists to join me in doing this type of work.
Oh, I think you're probably on that path. It sounds like it to me.
I hope so.
Here is a question from Twitter from Anita. What do you think are the best ways for health scientists to disseminate their research in a way that increases public trust?
Accuracy. And I have to say here that in part, doing research for this presentation and looking at some of the conflict that have arisen over COVID, in particular the problem of the mask, I wanted to show the discussion, for example, why early on they were saying masks are bad and later on they were saying it's good. And I wanted to have that interaction like I had for Dr. Fauci. And when I went digging, what I found actually is that they were quite accurate. A lot of the statements that we see the media report as being very, very short and very clear one way, mask bad, mask good. If you actually go to the original press conference that they lifted these things from, the press conference was maybe an hour. And back and forth, the person would go, well, there is this aspect and we're concerned about that, but there's also this other thing. So the discussion was more nuanced when you showed the whole press conference. And that's the problem. In a world where we have limited number of characters for each tweet, where we communicate with very curt text messages and media wants to have these headlines, it's just not possible to convey in that format accurate science. And that's what's needed. What's needed is to refuse to participate if things are not going to be represented accurately. And I've made that mistake before. I've participated in a news interview. They shortened what I said, and by the time it was shortened, it was no longer correct. And what they thought they did is they simplified the message. But they hadn't. They had actually changed the message, and they don't have a sufficient understanding of the problem to realize that the statement I made and the statement they changed it to were actually completely different. So in some cases, it's really the fault of the researcher for trying to simplify their message too much. But I also find that the media carries a big burden here in trying to state things simply. And it's, there's some things that can't be said simply. And if you feel you don't have the time to explain it correctly to the audience, then don't raise it at all, because it is far worse to pretend this is what the experts say, when in fact the expert was much more nuanced in their statements. But that being said, we do get expedient sometimes. We speak too fast, and we really have to make an effort to correctly qualify everything we said. I prepared more for this presentation than I have for most presentations, because I wanted to make sure that none of my words were out of place. And I hope I succeeded. Maybe I'll regret it when I watch it later. But it is difficult, but it has to be what we really work on hard.
Thank you. And another question from Twitter. This is from Allison Rose. What did you do at Los Alamos, and how is that connected to what you're doing now?
Well, my years at Los Alamos were basically my best years of my life. This was my postdoc year, so after my PhD. Well, actually, it was the end of my PhD and start of my postdoc, and it was in the lab of a gentleman called Alan Perlson. And he's basically the founder of in a sense, virophysics. He's been doing it way longer than me, and most of his work is known for HIV, where they were building these mathematical model of the virus that was being sampled from patients in HIV, and they were able to show that even though people believe HIV was replicating very slowly, that actually in reality HIV was having a very quick turnover that was rapidly suppressed. So even though it looked like it was bubbling away slowly, what was actually happening, it was surging amounts of virus being harshly suppressed. And so it looked like it was low, but it's because there was too very strong pressure. And what that means is if the virus production is high, the chance of mutation is high. And so this type of mathematical model really showed that you could get more out of the data than just by looking at it, right? And you could get insight that was very important to health. What I did back when I was working in Alan Perlson's lab was influenza. And that's been most of my career since then, actually. I've been doing a lot of work in influenza because back then I just thought influenza would have more data than other diseases. But then avian influenza happened and it became very crowded, actually, as a research field. I thought I'd found my nice little niche because everybody else was doing hepatitis C and HIV. So I thought influenza will be this nice, quiet place for me to do research. But it turned out differently. So, yeah.
Oh, thank you. Let's finish with this question. I understand that you've been immortalized in a cartoon, and I think the team found some interesting footage. Can you tell us more about it as they put it up?
Oh my God, yes. So this is the very best thing about getting my new position in Japan is that as part of getting this position, they actually made a cartoon of me. Yes, that's me. Oh my God. And so this is each of the deputy program director has a little cartoon version of themselves. And the bubble is actually my equation. So it's the virus replication. So my equation, meaning my group's equation for virus production by infected cells. So you can see that C there, C, TCID 50, that's the clearance rate I was talking about, the rate at which virus loses infectivity. So this is, yeah, awesome.
Oh, that's great. Well, congratulations. Cartoon, you know you've done it when you become a cartoon.
That's right, once you're a cartoon.
Dr. Beauchemin, thank you so much. Thank you for sharing with us today. Thank you for your commitment to outreach and to sharing the importance of science the way you do. That passion's gonna go a long, long ways. We really appreciate it. So thank you very much. To our online audience, thank you for joining us. It's always a pleasure, and we will see you again in a month. Take care.